Hello, it's David Leroy here, and in this slide presentation, I'm going to talk to you about some of the basics that you would need to be starting to learn about in order to understand the logic behind experiments. I suppose the most simple type of analysis that we're sensitive to is something that's called correlation. You know, when two things measured together seem to provide some sort of pattern. And if you have a look in the graph here, what we've got is a really simple correlation that I conducted. And these are the weights of various wood logs that were weighed when they were freshly cut, and then they were weighed again some months later. So they were freshly cut in September, and then they were weighed again in May. The weights were measured both times, and you can see in the chart that there's a pattern to those weights. They seem to be linear. The weights in May are all lower, and you can see that there's a correlation there between the time and the reduction in weight of each of the logs. Now, we're sensitive to correlations in lots of different aspects in life, and it's something that comes naturally to humans to be aware of. But from a scientific perspective, correlations technically do not prove causation. And so that is true, that it doesn't prove causation, but correlations can still be very useful things. So when people started to become concerned about the relationship between cigarette smoking and various types of cancer, that began as a correlation. People that smoked more tended to get more cancer, and the tobacco industry, of course, would have said, well, that doesn't prove causation at all. You need to be able to experiment to be able to prove causation. But logically, you would take a correlation like that really quite seriously. Even though it doesn't prove causation, it can still be a very good indicator and stepping stone towards being able to get additional scientific evidence. So going beyond correlation is experiments, right? And the goal of experiments is to find this causal relationship between different variables. And the logic behind an experiment is that you want to, change something to produce another change. And that is something that becomes under the control of the experimenter. So the experimenter directly introduces changes to produce a cause and effect relationship. So you want to make something appear, you can make something disappear, you can make something appear again simply by altering variables in an experiment, and then that gives you an idea that you are now that you now have control over a particular variable. There must be no other cause for the change being observed. So that's a technicality. You need to be able to rule out alternative explanations. And the one that is the greatest threat is, of course, including a confound that you're not aware of. But the general logic behind experiments is to go further than simple correlation to be able to find causal relationships between different variables. And so the basic logic of an experiment, here, if you take this example, imagine people are suffering from an illness called XYZ, and you want to see if a particular type of medication is going to alleviate those symptoms. Will people recover if given the medication? You could think in a really simple way that you could get a group of people suffering from this mysterious illness called XYZ. You could give them medication, then you could go and look and see if they recover. Now that in itself is a good start, but the good thing about experiments is that they include control groups, and it is probably important for you to ponder what the addition of a control group to an experiment like that would bring. If you just had the experimental group and gave them medication and then saw if they recovered from illness, you couldn't really prove that it was the medication. They may have recovered from the illness anyway, right? So the logic of having the control group is that you can also look at what happens when no medication is given as well. So some other concepts to be aware of, we've talked about this a little bit before, is the population, and that's an important consideration when you're conducting an experiment or trying to design an experiment. So populations are all the members of a specific group. So it might be that you want to find out things that can be applied to school-age children. But sometimes these need to be defined a little bit better for the purposes of experiments. So it might be school-age children between the ages of 4 and 17. You might be interested in studying people who smoke cigarettes, but you would need to define what it is that you're looking at in that population. So smokers, it can be quite a broad constituency of people. Some people might not smoke many cigarettes, some may smoke a lot, so it might be that you want to define your population of smokers a little bit more narrowly. You might say, well, we're only interested in looking at people in this experiment who smoke more than 20 cigarettes per day. Now, a sample is something that is a subset of a population, and that's what you need to select to be able to study, and the sample needs to be representative of the population that you want to study. And that's a really important thing for you to ponder as well. And is something that is really important, particularly in psychology, to be aware of, is the overlap or the representativeness of the sample versus the population. So the idea in a particular study might be that you want to study eyewitness memory, people who are eyewitnesses to a crime, right? So anyone in society could potentially be an eyewitness to a crime. And if we want to study how well eyewitness memory works, we need to choose a sample. Now, it's probably something that you're becoming aware of is when you start looking at, what the idea of an experiment is, what's the target population that you're really wanting to generalize to. You're probably starting to look quite closely at the sample, and in particular with eyewitness memory research, what we notice is that we want to learn about eyewitnesses in the population, but we tend to study university students because they're easily available. So we test their memory and then we make statements about eyewitness memory in general. And that's a good thing to point out if you're trying to provide some critical analysis, but it's not enough. You need to go beyond simply pointing out the difference between, or the potential difference between a sample and a population. You need to go further and also tell the reader how that might have affected the results. How might our conclusions need to be qualified in respect to the sample itself. A feature of experiments is also random sampling in an ideal world. So you need to be able to select whatever sample that you've got in an unbiased manner. And so all members of a population have an equal chance of being selected for the sample. Now that's something is also important to ponder, especially in relation to psychology studies that you are reading. How were the samples collected, and is there any possible limitation that will impose on the conclusions that you're able to draw? So the sample you choose for an experiment is very important for the generalizability of the findings. Also, it's worth understanding and being aware of descriptive versus inferential statistics, right? And these are often types of statistical information that we extract from data that we collect. On the one hand, we have descriptive statistics that summarize the data. So that will give you averages, standard deviations, and so forth. And then we have inferential statistics, which underpin the statistical analyses that we're going to use to determine whether there are significant differences between different conditions in your experimental design. It's also worth bearing in mind that descriptive statistics like the average, standard deviation, standard error, mean, median, and so forth are actually used to create inferential statistics. So there is a relationship between descriptive and inferential statistics. Again, it's important to be aware of the concept of dependent variables. These are the measurements that you're going to be taking in a particular experiment. And the dependent variable differs from what we refer to as independent variables, which are the different conditions in a particular experiment. So the dependent variable is really just the data point that you're going to record. So it might be that you're going to record people's heights or weights, and then that would be the dependent variable. Another way to think about that is the observations that you're making as an experimenter, and it can be helpful to think of the dependent variable as the thing that you're measuring that depends on the participant. It's not something that you're necessarily going to be able to control. It's what you're interested in finding out. So what's a dependent variable? Here's a couple of examples. Just imagine you want to compare the heights of trees between London and Birmingham. So you measure the heights of trees in each location and calculate the average height. So before you do that, of course, if this was an experiment, you'd need to give some thought to the sample. Which trees are you going to select to measure? And then what's the dependent variable in that situation between the comparison of heights of trees between London and Birmingham? Well, you've got choices here. It could be height in feet, height in inches, could be centimeters, meters, and so forth. But all of those would be suitable dependent variables to answer a research question of that nature. So another example, a product testing company has been asked to find out whether people prefer pineapple or marshmallow smelling shower gel. They ask 1,000 people to smell both and ask them which one they prefer. So what's the dependent variable? Well, what are you measuring? You're measuring their choice or their preference. So the preference, if you were to put the shower gels in two containers, one labeled A, one labeled B, the dependent variable would be the choice. So whether they've chosen A or B. Imagine you want to examine the gender pay gap and collect the value of salaries of 500 females, 500 males. You can calculate the average salary for males and females. So that means the dependent variable is the amount of salary, right, that, from each that you've measured from each individual participant. And that allows you to calculate the descriptive statistics, which is the average, and then from there you can go on, once you've calculated standard deviation, create some inferential statistics around that too. Another example, you want to examine the gender distribution in different programs at Royal Holloway University. For each program you count the number of different genders. What's the dependent variable? The dependent variable would be the genders that you're measuring, and you would end up with data that would show you the different, for example, percentages of people of different genders in each of the different programs that you wanted to examine. Another important idea when you're considering experiments and trying to design them yourself is this concept of operationalisation. And there's another concept that goes along with it called conceptualisation. Now, often your research question will revolve around a concept, right? And then the experiment has to operationalize that in some way. So you may need to create an operational definition of your dependent variable. And there's quite a lot of things that psychologists are interested in that there's not really any direct way to measure. So if you think of things like honesty, love, IQ, memory capacity, health, I mean, these are things that can really only be measured indirectly, right? And how well the overlap is between the operationalized variable and the concept is going to be an important consideration, especially in the research that you're reading, if you want to be able to provide your own critical evaluation. So in these cases, there are a number of things to think about when you're operationalizing your variables. So one, you've got to think of the property of interest. So what is it? What's the concept that you're trying to measure, right? And you need to be able to define that. And then what is the dependent variable going to be? How are you going to depend it and measure it? And the choice of your dependent variable is very important, and it must, if you can, have a good overlap with your concept, what you're conceptually trying to achieve. So this can be a little bit tricky. So I mean, if you think of a research question, which is obviously hypothetical, do hippies love trees more than lecturers? How would you operationalize love? Right, and if you take a moment to do that, okay, if someone told you, well, go find out, do hippies love trees more than lecturers? You'd be probably trying to find a sample of hippies. You'd want to find a sample of lecturers. You want to ask them something about trees. How are you going to operationalize love? Well, it might be how much money they've spent on trees in the last 12 months. It could be their rating on a 1 to 7 rating scale, with 1 being, don't love trees at all, with 7 love trees a great deal. So what would be a good operational definition, right? So you need to think about that and think about which is truly going to be able to measure love. Reliability and validity are also very important to be able to consider when you're designing your research. So validity is the idea about how well your dependent variable is measuring what it's supposed to. And if your dependent variable is measuring something else, that's going to be a threat to the integrity of any experiment. So it's important to have a good operational definition. So a DB is reliable if it gives you the same measurement, right, and contains minimum error. So here's a question for you. A set of scales used to weigh logs is out by 100 grams, right? So it's always going to give you a slightly lower reading than how they really do, how much they really do weigh. So is that reliable, or is it biased? The answer is, well, it is biased because it's consistently underestimating possibly the weights of the logs. But is it reliable? The answer is yes. So you will still be able to tell if the logs have started to dry over time, but it's going to be a biased way of measuring, but it is still reliable because the measurements you take will all be consistently underestimated. So unreliable data could introduce errors and can lead to incorrect conclusions. So it would be unreliable if sometimes the scales were 100 grams out and sometimes they weren't. So then you would have a pretty big error in your study. So good DVs are valid, reliable, and unbiased. It's also important to be aware of floor and ceiling effects. So imagine if you want to test a new drug that enhances memory. You've got 2 groups. One get the drug, control group receives a placebo. You show participants in the study a list of 4 words, test their memory for those words in an hour, and lo and behold, you find out that both groups get 100% on the memory test. So what's the problem with a study like this? Well, it might not be a very good test because it's too easy, and this is what we refer to as the ceiling effect, right? So a good psychological study would give some consideration for the difficulty of the task that's required to be able to allow you to see a possible difference between 2 different drugs that have been used. Floor and ceiling effects. Again, floor effects is when the task is too difficult, and so that would be some sort of situation where it doesn't matter whether you're in the condition that's got the drug or not. The task that you've been asked to do is too difficult that both the experimental and control conditions can't do it at all. And that's in contrast to the ceiling effect, which we've just discovered. You want to not have floor and ceiling effects within your studies. So every dependent variable is a type of data, and the type of data that you're collecting determines what sort of analyses that you can do. And here's a little chart that I've made for you to be able to see some of the differences between different types of data. So there's lots of data you can collect. Think of the examples that we went through before. And some of those examples referred to numerical data. So it might be that you're measuring the salaries of individuals in a population and sample. And sometimes it might be categorical, what genders of people are on different programs. And then when you've got categorical data, a lot of the time this will allow you to do non-parametric testing, whereas numerical data would allow you to do parametric testing. But there is a little bit of overlap in what you can do, and you'll see that when you're reading psychology studies. But generally, when you've got categorical data, that can be broken down into two further categories, ordered and unordered. So if you think of categorical data, it could be something like military rank. So it might be that you start off as private, sergeant, general. So it's rank, it's different categories, but there's a relationship between the different categories. You're all increasing in rank. Or categorical data can be unordered, so it doesn't really matter. So political party would be one of those types of categories if you're asking people who they voted for. It's not that Labour, the Conservatives, the Lib Dems, for example, are in any particular conceptual order. And again, here I've just put a little bit more information there on those categories for you to be able to see. So numerical data usually comes in the form of some sort of number or interval ratio, whereas categorical data, if it's ordered, we call it an ordinal scale, and if it's unordered, we call it a nominal scale. So the units of measurement. Interval scales. So there's an extraordinary number of different units of measurement that people use in various experiments, but these are things that, as I've said, that you can get a number as your data. So it could be things like response time, temperature, numbers of words recalled in lists, distance between points, and so forth. Now, an ordinal scale, these are categories, so it could be rankings of different football teams, different military ranks, and so forth. But if it's ordinal, you can say one is better than another, but not by how much. So ways to measure these sorts of things would be scales of 1 to 7, for example, unsatisfied to satisfied. But there is no necessary increment between 1, 2, 3, 4, 5, 6, and 7 that is necessarily equal. Nominal. So these are labels for different categories. So, like I said, different political parties, but nominal ratings could be measuring different eye color, right? So maybe you're interested in different eye colors between people in London and Birmingham, and you're just going to score those as 1 equals blue, 2 equals brown, 3 equals green, etc. So there's no real relationship between 1, 2, and 3. All they're doing is allowing you to note down for your dependent variable different categories that you're interested in. And so we can leave it there. That's just a short presentation to get us started on some of the important concepts to do with understanding experiments.